Okay, let's start. Today we'll learn about spatial autocorrelation, and we are going to measure and detect spatial autocorrelation in OLS residuals. There will be a short lecture, then we are going to move to R and R Studio. And at the end of this class, I will tell you about your research project, that is your exam. Okay, let's move on. Let's recall spatial data, how we can display this on the map. For example, this is a map of St. Petersburg, house prices. Cheaper districts are in green, and expensive districts are in red and yellow. We can see that the color distribution is not random. Green colored districts are close to similar ones, and bright yellow and red districts are close to similar regions. How to measure the intensity of interaction of neighboring regions. Let's have a look at this example, this simple example. 3 pictures with rectangular cells in black and white. In figure A, we can see that all the dark cells are together. In figure B, we can see that some of them are apart and distributed within white cells. And in figure C, the randomness is higher in comparison with the first figure. So we can say that figure A corresponds to higher spatial interaction case. How to measure this? We can introduce spatial autocorrelation. A week ago, we have considered a global index of spatial autocorrelation. Let's recall this. We introduce a global index of spatial autocorrelation in order to measure, in order to have a number to measure the degree of similarity between spatially close regions. The global index of spatial autocorrelation summarizes the phenomena of interest as a single value. Global indices do not reveal spatial clusters, but they detect the presence of a general tendency to clustering within the study area. The main idea to construct a spatial autocorrelation index is to use the correlation between the initial variable, say y, and the spatial lag of it. So we assign different weights for our neighbors, and then construct a linear combination of weights and values of the variable, And then we measure spatial autocorrelation. And we say that spatial autocorrelation is positive when similar values of a variable are located together geographically. And we say that spatial autocorrelation is negative when the dissimilar values of a variable located together. In the absence of spatial autocorrelation, it can be considered that the spatial allocation of the observations is random. So the main focus of our interest is positive spatial autocorrelation. This is the procedure of the computation of a global index of spatial autocorrelation. Compute or define the degree of similarity between every possible pair of regions with respect to the numerical variable of interest. Then we weight, that is, multiply each value by degree of proximity. Then we sum up all the products and divide by the total by a constant of proportionality. And the greater the number of regions that are similar with respect to y and spatially close, the greater the value taken by the global index of spatial autocorrelation. We introduce two global indices of spatial autocorrelation, Moran's index and Garrys Index. Moran's index of global spatial autocorrelation is this formula. We consider almost as the common index of correlation, but we consider only one variable. In this case is variable y, and we consider neighbors for each observation. And we use spatial weights indicating spatial interdependence between neighbors. The index varies from -1 to 1, and 1 is the case of positive spatial autocorrelation, and -1 is negative spatial autocorrelation. In order to test whether the spatial index is statistically significant, we introduce the null hypothesis, that is, there is zero spatial autocorrelation, that is, y is equal to 0. This means that the neighbors do not co-vary in any particular way. For example, if my region's value changes, my neighbor's values do not change. This corresponds to the null hypothesis of zero spatial autocorrelation. Under this hypothesis of no global spatial autocorrelation, the expected value of the index is as follows. A very simple formula, -1 divided by n-1. Let's consider also the Moran's diagram to interpret this index. I jump to this figure. Let's consider the median income in Paris census districts. This is a map of Paris, the capital of France. In the left figure, you can see not real data, but simulated random distribution. So no significant pattern of neighbors dependence. We can see that uh, yellow regions are close to red regions and vice versa. So that is no spatial dependence, no spatial autocorrelation. But the real distribution, which is the right figure, shows that red regions are close to red ones and yellow regions are close to yellow regions. And we can say that this picture should correspond to the higher spatial autocorrelation index. To interpret the spatial autocorrelation, we can use the Moran's diagram. We use spatial weights, we use the initial variable, and we construct the spatial lag of the initial variable. The horizontal axis corresponds to the median income by districts, median income, and this is centered and demeaned. And the first quadrant includes districts with high income and surrounded by high income districts. This part consists of high median income districts surrounded by low income districts. This part corresponds to low income districts surrounded by low income districts, and so on. So the positive spatial autocorrelation case is that many districts with high income are surrounded by high income districts, and many low income districts are surrounded by many low income districts. So surrounded by similar values. And this is an explanation we just ran through. Also, you can see different simulations with different coefficients of Moran's index. For example, the last figure, this one, corresponds to the index 0.9. And we can see that there are obvious clusters of high-income regions and low-income regions. And we also can see that for the case of 0.6, we cannot distinguish so huge clusters, and also we can see how the value declines when we permute the regions.
Excuse me,
Yeah.
I've got a question. If our index is equal to 0, that means that our values are distributed randomly, right? And if our index is below 0, how can we
If
understand
data
it?
is negative, this means that rich regions are surrounded by poor regions. For the case of negative spatial autocorrelation, we get um, a line going through the second and the fourth quadrants. So this means that rich regions are surrounded by poor regions, and poor regions are surrounded by rich regions.
Okay. Mhm.
Negative slope of this diagram.
Because on the
Yeah.
on these pictures, it is hard to understand the difference.
Uh, these two are close to 0, and when you look at this figure, this map, you can see that uh, the uh, the contrast, that is neighboring regions, rich and poor, the contrast is a bit higher than just randomness for these two cases.
Ah, okay. Now I can see it
Rich and
after
poor,
some time of observing.
uh, yeah, this is not the best way to distinguish randomness or contrastness. So we will compute numerical value to measure the spatial autocorrelation. This is an example for the previous maps, Moran's diagrams corresponding to the previous maps. This is for the positive case of spatial autocorrelation. This is for the negative case of spatial autocorrelation. Okay, let's go on. I will skip this slide. And one more index to measure the global spatial autocorrelation is Garrys Index. For Garrys Index, we compute differences between neighbors, and the null hypothesis, so the zero hypothesis, is that the differences between neighbors have no particular structure. For the case of Moran's index, we said that neighbors do not interact. Let's have a look at a couple of examples for Moran's for the choice of spatial weight metrics and for the choice of regions. all the indices depend on the choice of spatial metrics. We can define neighbors in many different ways. We can say that we consider as neighbors those regions that have a common border or not far from our region than, for example, 5 kilometers or 10 kilometers and so on. We can define the neighbors in many different ways. And the indices depend on spatial weights. Also, they depend on aggregation scale. For example, if we consider instead of subjects of federation in Russia, municipal regions, we can get different result. This is an example of considering different weight matrices for Paris medium income. Queen contiguity matrix, root contiguity matrix, one nearest neighbor, three nearest neighbors, Delaunay weight matrix. We can see that the Moran's index is different. Which is more important? What is more important is its p-value and the conclusion, whether the null hypothesis is rejected. When we reject the null hypothesis, then we say that there is a statistically significant spatial autocorrelation. For all the cases of spatial weights, the zero hypothesis is rejected, so we can say that there is strong and positive spatial autocorrelation in medium income. Also, we can consider different aggregation scale. For example, instead of small parts, we aggregate them and divide the city into 10 or 15 parts. And also for this case, the value of index is different. For both cases, this is the aggregate for the region, iris, and arrondissement. For both cases, we have significant and positive spatial autocorrelation. For different spatial weights and for different aggregation scale, the median income in Paris is spatial autocorrelated. And this is an example with Moran's scatter plots, Moran's diagrams for different aggregation scales. For both cases, we see that high-income regions are surrounded by high-income regions, and low-income regions are surrounded by low-income regions.
Excuse me. And are we able to somehow make a mistake while choosing our aggregation scale? So can we choose the one that will change the current link?
That's a good question. Thanks. Actually, the indexes, depending on the area shape are subject to dependence on the shape. And this is a problem of MAUP, or modifiable area unit problem. I will briefly say about this in a week.
Okay, thank you.
Usually, if you have data on more disaggregated units, it's better. For example, if you have data both for regions and for the country as a whole, it's better to work with regions instead of one number, one value for the whole country.
Okay.
In order to compute spatial autocorrelation index in R, you can use a package SPDEP. Also, I recommend you to have a look at Bivand's handbook on spatial analysis in R, section 9.2 and 9.31, spatial neighbors and spatial weights and global tests. Let's jump to the regression. Let's start from the multiple regression for the non-spatial case. You know that about residuals, there must be some assumptions, and you can compute OLS estimates to find the estimates of the parameters for beta, for gamma, and then you can compute OLS residuals for each location. There's nothing new for now. And we can check whether residuals are spatially autocorrelated.
Excuse me, could you please remind us what is OLS?
Ordinary least squares.
Ah,
МНК метод наименьших квадратов.
okay, thank you.
Я не знаю, как у вас называлось. Где-то чаще постоянно говорят ОЛС, где-то чаще МНК. Метод наименьших квадратов. Okay, we estimate beta. We estimate beta is a scalar and gamma is a vector. We estimate them using the ordinary least squares method. Then we compute OLS residuals for each location, for each observation. Then we construct spatial weights for each observation, for each location, and test whether residuals are spatially autocorrelated. By means of this test, we can check whether they are independent spatially. That is, we apply, for example, Moran's index to residuals. We just replace for variable y by our residuals. And we know that the mean value is 0 for residuals, нулевая средняя для остатков. Then we rewrite this formula, and the procedure is the same. Then we compute the test statistics and compare it there are some sources for you. For example, this source B1, the applied spatial data analysis with R. And also I recommend you to watch video on spatial autocorrelation and weight matrices. So this is a lecture by Luke Anselin, one of the big guys in spatial econometrics. And there is a link to spatial data sets. Now let's switch to the R Studio. I need to open this.
Will we use the previous file or another one?
The new file is in LMS. You can just copy and paste.
So where can we found? Okay, I see. So a big text file.
I'm sharing my screen with RStudio. Let's start from the beginning. We work with the same spatial data set on liquor demand from the article by Mark Borky on geographic access and demand in the market for alcohol in the review of regional studies. There is a data set on liquor consumption and some social and economic indicators of counties in North Carolina and Virginia states. The data is a shape file of polygons of counties. Also, there are geographical coordinates on longitude and latitude of counties, centroid. There is a variable on liquor sales per capita income, commuting time, and so on. Also, there is variable DUI, which is driving under influence, which is in Russian вождение в нетрезвом виде, driving under influence. Тут, видимо, не только нетрезвое, еще что-то. What we are going to do? We are going to measure spatial autocorrelation for different variables. Then we estimate using OLS a regression. Then we measure spatial autocorrelation in residuals of OLS. So let's start from the previous part. We include different packages, then we set working directory, then we read in a shapefile, then we just have a look at the data structure, which is a spatial data set.
By the way, remind us, please, where can we find the variable description? It was in another text file, right?
Yeah,
Okay, I see.
let me attach this. Just a second. I'm adding the variable description to LMS. Now you have it in LMS just after the code for today.
Okay, thank you.
Let's go back. We read in a shapefile, NCV ACO SHP. Then we call it regions. Then we have a look at the attribute table. Then we can have a look at each variable separately. Then we check whether there are string variables that should be fixed. Then we apply as numeric function. Then we assign a projection. Then we test this. Second. We can plot the map. And also we can reproject this. Let me recall what is reprojection. Представим, что у нас $10 США есть. Мы же не можем просто переназвать валюту рублем и сказать, что у нас 10 рублей. Нужно перепроецировать, то есть переконвертировать валюту, чтобы получить эту величину в рублях. То есть нужно умножить на какой-то коэффициент. Это будет конвертация валюты. А если мы говорим о координатной системе, то перепроецирование. И вот здесь assign мы просто переназвали, назвали эту проекцию таким-то названием, ВГС-84. А здесь перепроецировали, то есть пересчитали, и раньше у нас были в градусах, теперь в метрах или в километрах. After that, we can plot the projected spatial data set. Then we start creating neighbors. A week ago, we learned about queen and root contiguity, and now we can create first list of neighbors, just numbers. For example, the first region have 4 neighbors: region number 8, region number 25, region number 60, and region number 111. Then we can have a summary on the list object, number of regions, link number distribution, and so on. Also, we can define another type of neighbors, root contiguity, and have the same type of summary on this. For our shapefile, they are not the same. Queen neighbors and rook neighbors are different. Based on the neighbors list, we create spatial weights.
Excuse me. Could you please clarify? So summary are the same using queen and rook approaches, but it is not true in our shapefile. How does it work?
Summary has the same structure, but they are different in values. For example, summary queen and b, number of non-zero links 1132, and for O contiguity we have a different number of non-zero links, because those regions that have only one common point, they are not neighbors for root contiguity. Если только одна общая точка, то для root contiguity они не являются соседями. Для queen contiguity соседи, поэтому у них отличаются. И когда мы проверяем, используя функции isTrue, all equal for both lists of neighbors, we get that the result is false. They are not equal. Then
Okay. Thank you.
Then we create spatial weights based on the two lists of neighbors. Queen weights, we transform it to weights list using NB2 list. This object is a list, it's a type of list, consists of the neighbors lists itself. Then there are weights, equal weights for each set of neighbors for each region. Then we compute Moran's index of spatial autocorrelation for a per capita income using Queen's spatial weights. And we get that the coefficient is 0.66. Then we can.
Excuse me.
Yeah.
Uh, could you please clarify what those indexes are used for? So, how can we interpret them?
To interpret this, we can, for example, run this line, and we get Moran's scatter plot or Moran's diagram. A horizontal axis corresponds to per capita income in counties. The vertical axis corresponds to spatially lagged per capita income in counties. So we can say that there are many counties with high per capita income that are surrounded by high income counties, and many low income counties are surrounded by low income counties. And the slope is positive. This corresponds to this value, Moran's index of spatial autocorrelation, or this one. So there is statistically strong positive spatial autocorrelation. We compare this value with the expectation. This is greater than the expectation. And also we can find the p-value for this, which is close to 0. So we observe positive spatial autocorrelation in per capita income in counties. We have revealed this using Moran's index of spatial autocorrelation. And also,
And as for the next coefficient k, do we use it or not?
K, this, let me open the help page. This is a sample kurtosis of X. Скошенность исходных данных.
Okay. So it's not the coefficient on the Moran graph.
No, we do not interpret this using Moran's graph.
Okay.
Let's test. Let's test another variable using the same spatial weights. Sales per capita, alcohol sales per capita in counties. The index is minus 0.01. Also, we can run Moran's test. Also, we can plot. Just copy and paste, replace the variable name. And according to this Moran scatter plot, we cannot say that there is strong negative or positive spatial autocorrelation, because the slope is close to the horizontal axis, we cannot distinguish that there is a spatial pattern of sales per capita distribution.
And
That is,
mhm.
yeah.
And can we do some kind of significant test for those coefficients?
Sure. P-value is greater than 0.05. То есть если сравнивать с привычным нам уровнем значимости 0,05, смотрим на p-value, он больше. Поэтому у нас нет основания отклонять основную гипотезу о незначимости индекса Морана. То есть нет оснований отклонять предположение о том, что отсутствует пространственная взаимозависимость. Okay, so we have considered two different cases. The first one is for per capita income, which demonstrates a strong pattern of positive spatial autocorrelation. And the second one is variable sales per capita, which is not significant. The Moran's index is not significant. Let's check whether we have the same using different weights. I just copy and paste and change, and I'm going to replace queen to rook. Copy this and paste. And instead of queen, I use rook. Rook. Then I run this part. Oops, sorry. We don't have rook weights. Let's create this. I have created rook weights. Then I run these lines and I get that per capita income is also spatially autocorrelated for this type of spatial weights. And the Moran scatter plot confirms this. For the second variable, sales per capita, I change this. Rook. For the second variable, I get almost the same values, and p-value is 0.5, and I cannot reject the zero hypothesis that there is no spatial autocorrelation. Also, you can use these procedures without defining weights directly, but we can use NB2list W instead of a new object rook weights or queen weights. And also you can run the test using this expression. Now let's consider how to create weights, spatial weights based on a given number of neighbors. For this, we need to use a package rgeos. I run this line. To measure number of nearest neighbors, we need to use not polygons, but points. Когда считаем ближайших соседей, то есть заданное количество ближайших соседей, мы не можем это определить для полигонов, но для точек можем. Чтобы перейти от полигонов к точкам, мы можем использовать, например, центроиды этих полигонов.
Извините.
Mm-hmm.
So we assume that we can use centroids.
Yeah.
So we need to get points from our polygons.
Yeah, exactly. First, we construct centroids that is for each polygon, for each county, we compute one point with longitude and latitude, which is a centroid. For this, we can, for example, use, let me open the description. For this, we can use longitude and latitude of county centroid. We can use directly this data, but for the case when you don't have it, you can use this function gcentroid. Let's run this. Regions centroids. And you can see that this object consists of coordinates, longitude and latitudes, and variable and object names. Okay, let's have a look at this. The class of it is spatial points. There are well, there is some information on projection, datum, minimum and maximum values for coordinates, which is not very important for us. What we use from this is nearest neighbors. This is function of this object, regions centroids. We set up a number of nearest neighbors, and we say that we use a geographic longitude and latitude. For the case when we create points based on the projected shapefile, we need to put here false. This shapefile is not projected. this is in longitude and latitude, so we use this one. And also we indicate that row names are this variable. Let's run this. We create neighbors list based on 6 nearest neighbors. Let's find this regions of 6 nearest neighbors. As usual, there is a list of neighbors. For each region, we have 6 neighbors, and there are a number of them. Regions 8, 19, 25, and so on. The same number of neighbors. Then we can have a look at the summary of this.
So,
Yeah.
am I right that we have changed our method of counting neighbors, but numbers are still the same, or not?
Not the same. We can open, for example, this part. Neighbors based on queen contiguity. For the first region, we have 4 neighbors. For the second one, 4, then 6, 6, 4, 5. You can see that there are different numbers of neighbors for each region depending on their location, because this weight, this spatial dependence based on queen contiguity, that is, we define regions as neighbors if they have at least one common point, not even a common border, but at least a common point.
Okay, and in the last approach, we just stated that we are searching for the 6 nearest neighbors. So we fixed the number. Okay, I
Exactly.
see.
When we use a given number of neighbors, this helps us to avoid spatial cases like islands. For islands, we get 0 neighbors. For rook contiguity case, for queen contiguity case, because there are no regions bordering with an island. But when we define neighbors based on a given number of neighbors, the problem vanishes. For example, if we construct neighbors for countries, for Australia, we have 0 neighbors based on contiguity, but we can define neighbors based on a given number of neighbors. То есть если у вас островные государства или регионы, то соседи на основе смежности границ будут давать нули, то есть у вас будут оставаться несвязанные регионы. В таких случаях переходить к заданному количеству соседей. And we can run summary on the list of neighbors. We see that the average number of links is a given number. number of least connected regions is equal to the number of most connected regions, which is quite obvious. Then we can compute Moran's index based on nearest neighbors weight matrix. Let's do this. Okay. I just copy this part. I call this regions, 6 nearest neighbors, weights. Copy and replace. Let's run the code. You can see that spatial weights are equal for all the regions. Every region has exactly 6 neighbors, and spatial weights are 1 divided by 6. Одна шестая все веса. We have defined spatial weights, then we compute Moran's index of spatial autocorrelation. Let's run test and let's create and display the Moran scatter plot. Also, we have that for this variable per capita income, we have a significant and positive spatial autocorrelation index.
Excuse me. So we decided to make a new model, making the 6 nearest neighbors as the only neighbors, or not?
We can define different spatial weights. For example, for now we have defined 3 types of spatial weights based on root contiguity, queen contiguity, and 6 nearest neighbors. For all 3 spatial weights, we get that per capita income is positively autocorrelated. Also, we can apply the 3rd type of spatial weights to our 2nd indicator. Now we just apply different spatial weights and compute spatial autocorrelation index.
So we just computed the weights according to the nearest 6 neighbors,
Yeah,
right?
yeah.
Okay.
We have defined a new set of spatial weights based on 6 nearest neighbors, and we compute the Moran's index. The next section in this file is how to draw a beautiful map. I'm not going to focus for a long time on this. I just run and show this. You remember how much time you have to spend using QGIS to define a plot, but for RStudio you cannot move this, you cannot change the map. You can use it just for just as an image. Also, you can color the map. And you can see per capita income distribution, which is first transformed as logarithms and then colored. So we can see that regions with high income are surrounded by rich regions, and poor regions are located together. And previously we have computed Moran's index, and the Moran's index was significant and positive, and this map confirms this. The next part is a global Moran's test for residuals. We're going to use variable names without any prefix. So I attach regions and data. То есть мы будем напрямую обращаться по названиям столбцов, without indicating from which table we are going to use them. I attach. Then I construct a regression with the dependent variable driving under influence. Вождение в нетрезвом виде, зависимая переменная. И составляем объясняющие переменные. Вождение в нетрезвом виде может быть объяснено следующими показателями. Продажа алкоголя, среднедушевые. Возможно, уровень образования может влиять, some college percentage. Возможно, расовые различия могут влиять, non-white. Возможно, религиозные различия могут влиять. And check this, ground to ABC. Weighted average distance from block group to nearest bar selling liquor. Расстояние до ближайшего бара. So we construct a regression. Then we estimate the regression using,
Excuse me. And do we have some sort of variables of interest here, or we just put them all?
First, we just put them all. The dependent variable is driving under influence, and we construct a set of possible explanatory variables. Then I estimate the regression using ordinary least squares, and I get the following results. Sales per capita are significant and positive. The higher alcohol sales, the higher driving under influence. Some college degree is negative but not significant, as well as non-white people percentage. Baptists percentage is significant at 0.1, and the distance to the nearest bar is not significant. We have estimated the regression, and let's check whether residuals are spatially autocorrelated. We can use one of our spatial weights, for example, Queen weights. I run global Moran's test for regression residuals. I get that the observed Moran's index is 0.2, and p-value is close to 0. That is, there is spatial autocorrelation in residuals. Also, we can get this using this procedure, the same value, and using Moran's plot. This means that regression residuals are not independent. So possibly we may have missed something spatially dependent constructing this regression. То есть, возможно, составленная регрессия не учитывает пространственную взаимосвязь, и нужно будет ее туда включить. Это мы на следующем занятии будем делать. Так, осталось минутки 3, и давайте я быстренько расскажу, что от вас будет ожидаться на экзамене. Экзамен, как я уже говорила, может выполняться в мини-группах до, по-моему, я указала, до 3 человек. Вам нужно будет составить мини-исследовательский проект, самим найти данные, самим поставить задачу, самим применить те методы, которые мы изучали, возможно, что-то дополнительное еще хотите изучить, никаких запретов, и рассказать об этом. Это может быть следующим образом начато. Находите датасет, кстати, открою слайды. Находите датасет, for example, spatial data sets from this web page. Let me share screen. There is a web page with sample data sets with descriptions. For example, Airbnb rentals, house sale prices, and so on. Вы можете начать с того, что посмотрите, что это за данные. Даже отрисовка есть на страничке. Описание данных, какие там переменные есть. Возможно, там будет ссылка еще на статью, в которой использовались эти данные ранее. Вам нужно будет составить карту, показать, как распределена в пространстве та или иная переменная, проверить, является ли эта переменная и другие переменные пространственно автокоррелированными, то есть можете использовать индекс Морана для этого, составлять различные пространственные веса и затем оценить пространственную регрессию. Это мы уже на следующем занятии, на следующей неделе подробнее рассмотрим. Есть ли вопросы?
А вы нам, может быть, в ЛМС выложите именно прям полное описание того, что должно быть включено? Ну,
Хорошо. Вернее, не полное описание, потому что все-таки там многое будет зависеть от того, какой у вас источник данных.
мгм.
В общих очертаниях, да, я распишу сегодня. Мгм.
Спасибо.
Еще вопросы?
Должна быть регрессия, да, пространственная?
Так, очень шумное эхо было.
Прошу прощения, секунду.
Мгм. А, Вопрос какой-то был или в чате напишите?
Да, Вера Ивановна, можно вопрос?
Да.
Должна быть обязательно пространственная регрессия, и нужно ли делать какую-то кластеризацию, да, то есть подсчет индекса?
А это зависит от того, какую задачу себе поставите.
То есть зависит от задания, хорошо.
Да,
Но регрессия должна быть, да?
зависит.
Тоже зависит.
Да.
Хорошо.
То есть здесь дается возможность проявить ваши исследовательские пытливые качества. Вот есть датасет, что он вам может сказать? Как пространственная взаимозависимость проявляется в этом датасете? О чем говорят пространственные данные? И что вы можете из них вытащить? О чем рассказать? То есть проводите анализ пространственный, и на этом будет, в этом будет заключаться ваш экзамен.
То есть строгих требований к методологии нет?
Нет, строгих требований нет. И мне бы очень не хотелось бы давать вам какую-то четкую процедуру. Первый пункт сделали вот это, второй пункт дружно посчитали все вот это. Нет, это, на мой взгляд, неправильно будет. Я не эти задачи преследую.
Хорошо, спасибо.
Подскажите, а презентация в каком будет формате?
Презентация чего? Вашего
Ну, да.
исследовательского проекта? Экзамена? А, Нужно будет краткий текст работы. Это не будет толщиной с курсовую или с дипломную работу, но кратко нужно будет описать на 3-4 страницы, скажем, что вы делаете. Если вы считаете в варе, то приложить код. Если что-то делаете в QGIS, то приложить то, что получилось со всеми нужными слоями.
А мы это будем именно вам отправлять, ну, или
Да,
еще и рассказывать? Вот такой вопрос.
сначала отправите накануне, а потом будете рассказывать, когда у нас по графику будет экзамен. А, То есть на выступление 10-15 минут каждой группе будет отводиться.
Мгм. Хорошо, понятно. Спасибо. То есть, ну вот, это финальное действие будет уже на сессионной неделе, то есть через 3 недели. Ну,
А
через
когда у
2,
вас
по-моему, да.
мое расписание занятий так, показывает, что после 11 октября у нас с вами больше нет занятий. Видимо, с 18, да, сессия у вас?
Кажется, да.
Да, похоже.
Ну вот 18, с 18 на неделе.
Мгм. Да, до 25. Да, окей,
Нам,
понятно.
получается, нужно что-то сделать к следующей неделе?
А к следующей неделе будет домашнее задание. Было мы запишем. Еще вопросы?
Тогда уже по домашнему заданию вы его как-то можете сейчас кратко охарактеризовать? То есть оно по ару или по гизу, или...
Ару будет по сегодняшним материалам.
Окей, оно именно сдается?
Да.
Или... Все, окей. Понятно. Спасибо.
Так, ну, наверное, все. До следующей недели. До свидания.
Спасибо, до свидания.
До свидания.